Good morning, ladies. So did anybody else get woken up by a tornado warning last night?
No, but my sister did. They had like 2 minutes to get in their shelter.
Uh, I was so tired I didn't even bother waking anybody up. So
Yeah, her phone was on silent and do not disturb, so she didn't even know.
Gotcha. Yeah, my phone was on ring, but it wasn't on ring. It was on vibrate, so I heard it vibrating. But I heard the sirens going on outside. So, but yeah, it only lasted like a couple minutes, so it wasn't too bad. But it was either get up and get everybody else awake and down into the basement, or just say forget about it. So unfortunately, I chose the latter. I feel like a bad parent, but that's fine.
Hey, it seems like it worked out. Everybody's fine. So
Exactly. Well, we've been through so many of these that, it's like, yeah, it's not going to bother anybody. It'll be fine. All right, so let me share my screen here. So I've been meaning to show you guys this for like 3 days now, but I keep forgetting because I'm just old, I guess. So this is a simulator. It's up on Blackboard, so you can find it under the in-class simulations. But what this thing will do is you can have different configurations, or you can draw your own configurations. And basically what it'll do is it'll draw the vector fields, or just the field lines, and the equipotential lines that we're going to talk about today. But for example, if I just have one charge here and I click on the field lines, it'll start drawing field lines. So you can see them radiating away in all different directions. And then I can also draw the vector fields. So here it'll draw the arrows as well. And again, the length of the arrow refers to the magnitude of the field. So the closer it is to the charge, then the longer the arrows. And then again, as you get farther on here, it looks more just like little specks. Or we can draw different configurations. So for example, we could have a dipole. So again, we can click on our field lines. So again, I'll draw the field lines. We could do the vector lines. So you can see what the vectors are actually doing. So again, pointing from the positive charge to the negative charge. Or as we're going to talk about today, is I'll also draw the equipotential lines. So you can get all these wonderful, beautiful type little shapes and things. We can clear all that. Like I said, we'll do all kinds of different things. This is what's known as a quadrupole. So we can draw the vector field lines, equipotential lines, and the field lines. So this is a nice thing to kind of play with. Like I said, I put it up onto Blackboard so you can play with it yourself to kind of see what does the electric fields actually look like for all these different charge configurations. Like I said, you can actually draw your own and everything as well, but they have squares. You can do double rows. This basically is your parallel plate capacitors. It's called a shield. So these charges here to shield the inside charge. You get into dipoles, rows of charges, all kinds of different stuff. So that's up in there. It's kind of fun to play with. You kind of see what's going on, how you actually draw these different lines and everything. So great. So that brings us to today. So today we're going to start the last chapter when it comes to this exam that's again occurring on Monday, which is chapter 17. Let me move all your faces over here. So chapter 17 is about electrostatic potential, which we've already basically seen in lab, and we're going to talk more about, and capacitors, which we also saw in lab. So basically the starting point of chapter 17 is it wants us to basically look at the structure of Coulomb's law. So remember that Coulomb's law says that the magnitude of the electric force is equal to the constant, the electric constant, times charge 1 times charge 2 divided by r squared. And compare that to the gravitational force, where the gravitational force is Newton's gravitational constant times mass 1 times mass 2, all divided by the distance squared. And to note that these two have exactly the same structure. Okay. Now, what's interesting about this, or important about this, is that this one that we know from 175 is actually a conservative force. Right? So, since this one is a conservative force and it has identically the same structure as Coulomb's force, all I'm doing is just changing variables, but it has exactly the same structure. What that should imply to us then is that Coulomb's force then is also a conservative force. So it wants us to note that Coulomb's force is also conservative. Now, what's so important about conservative forces? Anybody remember why conservative forces are important? What's the big deal of conservative forces? From 175? It's okay if you don't, but anybody remember? No, that's okay. So the special thing about conservative forces are that conservative forces allow us to then define a potential energy. So the fact that the Coulomb force then is a conservative force, what that means then is we can now define a potential energy based off of this Coulomb force. So that means we're going to add now another type of potential energy that we can have. So far we have spring potential, we have gravitational potential, but now we can have this new type of potential, which is then the electrostatic potential energy. So remember that potential energy we can define via work. So remember, work is equal to negative the change of potential energy. So we want to know then, what is the potential energy for this type of force? Okay. Now remember in general too that our electric force in general is simply equal to the charge times the electric field. So this is actually a generalization of this guy. So these two things are the same. So we're going to focus on this one, where this one we're going to pretend for now is a constant electric field. So to figure out then what the potential energy should look like, let's look at this situation. So let's take two parallel plate capacitors where this one is a positive charge, and this one has a charge of positive Q. This is a charge of negative Q, and we know that this is going to set up an electric field in between our two plates here, where that electric field is simply equal to a constant. So we have a constant electric field. Now, we're going to take a test charge, a positive charge here, stick it inside of these plates, and we know then that this thing is going to feel a force in exactly the same direction then as the electric field. So in this case, the force is going to point to the right. So let's say that these two guys are separated from A to B by a distance of D. And we want to know what is the work done by the electric field to then move the charge from plate A to plate B over this distance of D. Well, remember that force, or work anyways, is equal to the force times the displacement times cosine of the angle between the two. So this is our work. In this case, it's the electric force, so that's going to be Q times E times the displacement, where the displacement in this case is simply the distance of D, times then cosine of the angle. But remember, the angle is the angle between the force and the displacement, or displacement vector is in this direction. Our force is in this direction, so the angle between the two is simply 0, and cosine of 0 is simply 1. So what this says then is that the electric field does work by bringing this charged particle across these plates, which is then equal to the charge of the particle times the electric field times the distance. Now, since the work, though, is equal to negative the change of potential energy, what this means then is that the potential energy, or the change of potential energy, then is equal to negative of the work, which is then equal to negative Q times E times D. So this is then our potential energy. Now, let's talk about this a little bit. So what this says then is that this is the potential energy at B minus the potential energy at A is then equal to minus Q times E times D. Right? Because remember, change is the final minus the initial. So our final potential energy is the potential energy at B minus then the potential energy initially, which is potential energy at A, is then equal to a negative value. So what does that mean? So what that means then is what? How does the potential energy at B relate to the potential energy at A? Is the potential energy at B greater than the potential energy at A, or is the potential energy at A greater than the potential energy at B? So what do you think? What does this negative sign here tell me? What do you think? Which one of the two is bigger?
Would it be A?
It would be A, that's right. So what's happening here is that what? This is a region of high potential energy. And this is a region of low potential energy. Exactly. So what that negative sign means is that the potential energy at B is less than the potential energy at A, which then gives me that negative sign. So what this says then is that what? The electric field is doing work by moving this charged particle from a region of high potential energy to a region of low potential energy. Now, does that make sense? Well, yes, right? Because that's what the gravitational force does. So if I took this bottle and I let it go, then the gravitational force pulls it downward. It does work by pulling it downward by bringing it from a region of high potential energy to a region of low potential energy. So this is doing exactly the same thing that gravity does. So here I just have a charged particle which is moving from high to low, which is the same thing as dropping this mass to have it go from high to low. So what this tells me then is that regions of high potential energy are regions with positive charges, where regions of low potential energy are regions with negative charges. So these two things are telling me that the equivalence of the charges. So anytime I have positive charges, that's regions of high potential energy. If I have negative charges, then that's regions of low potential energy. Now, one thing to be careful about here, so let me put a red on here. This is only true for a constant electric field. If my electric field is not constant, then this doesn't work anymore. We would have to do the same thing we did in 175, which is cut it up into small regions and then actually integrates over the electric field. But I'm just going to leave it there that way for now. Okay. Now, it's actually more convenient for us to define a new quantity instead of working with potential energy and work with something which is known as the electrostatic potential. So what's the electrostatic potential? So the electrostatic potential is what we're going to call V. So hopefully you guys have picked up on this so far. I'm writing my V's differently. So when I write a V with two broken lines on top, this is my electrostatic potential. But if I write a V with a continuous line, this is equal to volume. And if I write a little tiny V with nothing on it, this is velocity. So hopefully you guys have picked up on that as I've been writing all these different things. But yeah, anytime I write a capital V with two broken lines on top, this is electrostatic potential. Anytime it's a capital V with a continuous line, that's a volume. And then I try to make a little v equal to velocity. So let's define electrostatic potential. So electrostatic potential, we're going to call V, is then related to potential energy by charge. So electrostatic potential is equal to the potential energy per unit charge, which means this thing has units of joules per coulomb. But joules per coulomb we simply call a capital V, which is what's known as a volt. Okay. So a volt then is the energy per unit charge. So this is how much energy it would take for me to move a charge across a particular distance. That's what this thing means. So this is the energy required to move a charge through a potential of 1 volt. Okay, that's what this thing means. So typically we call this electrostatic potential, but in short, we usually just call it potential, just to make it a little bit easier. Okay. So this means then that the change in potential, delta V, is then equal to the voltage at, say, point B minus the voltage at then point A, which is then equal to the change in potential energy divided by the charge. So this is what we call voltage. So voltage then is the change in potential between 2 points, which is equal to the change of potential energy across those same 2 points per unit charge. So this is what we call voltage. Okay. So going back to our previous picture, we'll do R. What this means is that here, this is a region of high potential energy, which means it's also a region of high potential. So this is a region of high potential. And then this is a region of low potential. So again, my object then goes from high potential to low potential, or high potential energy to then low potential energy. Now, the reason we usually talk about potential as opposed to potential energy is because if I know the change of potential, or the voltage, then I also know the potential energy, right? So this thing also tells me then that my change of potential energy is then simply equal to the charge times then the change in voltage. So what this means then is if I know the voltage difference between my parallel plate capacitors here, so if I know that this is at a voltage of VA, this is at a volt of VB, or potential of VA and a potential of VB, so that this has a potential difference or voltage of delta V, then this tells me exactly what the potential energy is. So from here, we would then say the potential energy then is simply equal to the charge times the change of potential, which then allows me now to use conservation of energy. Okay. So now that I have this, I can now use this into conservation of energy and say, well, the change of kinetic energy plus the change of potential energy, which is then equal to the change of kinetic energy plus the change, or Q times the change in potential, is then all equal to 0 as long as this is a conservative force. So conservative force. So there's other reasons why we talk about potential, and we'll get to there in just a minute, but let's use this and now let's do an example. Okay. So let's look at the first one. So the first one says, in the figure below, we have a charged particle, which is either an electron or a proton, is moving to the right between these two plates, which are separated by a distance of 2 millimeters. Pardon me. The plate potentials are, so V1, the one on the left-hand side, is negative 70 volts. V2 is then a negative 50 volts, so the one on the right. And what it tells us is that here at this point, the particle is moving at 90 kilometers per second. But then it slows down as it gets to the second one, okay? So basically what's happening again, it's moving at 90 kilometers per second, and then as it gets closer to the second plate, it is slowing down. So first part is it wants to know, is this in a proton or an electron? So meaning, does it have a positive charge or a negative charge? And then from there, we want to determine what is the speed of this by the time it reaches the second plate. Okay? So this is what we wanted. So let's kind of redraw our situation. So here is our first plate, where again, we're told this has minus 70 volts. Here is our second plate, which we know now has minus 50 volts. Here is our charged particle moving this way with an initial velocity equal to 90 kilometers per second. And we know is that by the time it gets here, its new velocity V is less than 90 kilometers per second. So we know it's moving slower. Good. Now, first of all, again, from this information, we want to know, is this an electron or is it a proton? Right? So we want to know, is it one or is it the other one? So first things first is what? So notice that, again, what we care about is the change of potential. We care about that voltage because, again, our potential energy change is equal to the charge times the change in voltage. So here, even though this is telling me it's negative 70 and this is negative 50, well, I can arbitrarily, if I wanted to, set this one at 0 and this one then at 20, because the change is still the same. Because my change here is 20 volts, my change here is also 20 volts, just to kind of see a little bit easier what's happening. Now, if this is at 0 and this is at 20, what I can say then is, well, this is actually my negative plate, and this is actually my positive plate, which means that I actually have an electric field inside of here, which points from the right plate to the left plate. Right? So this is actually my electric field. Which means in this case, my particle is moving from what? A low potential to a high potential. So my particle here is moving to the right. It is slowing down, which means, is this guy going to be a positive charge or a negative charge? So what do you think? So if you like, instead, of thinking about potentials, what's the direction of the force on this guy? So if he's moving to the right, but he's slowing down, what's the direction of the force? What do you think? Or a different question. What's the direction of the acceleration?
To the left?
To the left, good. So we know in this case, the force would be to the left. So again, we know it's moving from a low potential to a high potential, which means that it's going opposite the direction of what it wants to do, right? It's equivalent to me throwing this thing into the air, which means that since the force is in the same direction as the electric field, that charge must then be positive. So since the force is in the same direction as the electric field, this has to be positive to make sure these are in the same direction, which means that this thing has to have a positive charge, which means it has to be a proton. So since force is to the left, same direction as E, then it must be positive. Good. So now part B is asking, saying that what? Okay, so now that we know it's a positive charge, so we know it's a proton, how fast is this thing going by the time it reaches here? Well, to do this, we can use conservation of energy. We can now say that the change in kinetic energy plus the change in potential energy is then equal to 0 since there's no non-conservative forces. There's no air resistance or anything like that. So here we can say the final kinetic energy is 1/2 mass of the proton times the final velocity squared minus the initial kinetic energy, which is 1/2 the mass of the proton times the initial velocity squared, plus the change of potential energy, but our change of potential energy in this case is going to be the charge, which is the fundamental charge, since that's the charge of the proton, times then the change of potential, right? So here, the change of potential is actually going to be negative because it's going from what? Well, it's actually, no, it's positive. So it's final minus the initial, which is positive. So here, delta V is going to be equal to what, V2 minus V1, which is then going to be a positive 20 volts. And all that has to equal 0. Good, so from here, we can use this now to solve for the final velocity. So I'm going to add this term over here, subtract this term over here. So let's do that in steps. So I get 1/2 mass of the proton, velocity squared is then equal to 1/2 mass of the proton, initial velocity squared minus the charge times the change of potential. Finally, we're going to multiply by 2, divide by the mass, and take a square root. So we get the final velocity then is going to be equal to 2 divided by the mass of the proton times 1/2 the mass of the proton times the initial velocity squared minus the charge, which is the fundamental charge, times our change of potential, and square root it. So putting all that together, what we find in this case then is our final velocity turns out to be 65.29 kilometers per second. 65.29 kilometers per second. All right. Now, good. Let's do another example. So the next example says that we have an electron which is in a cathode ray tube. So this is a cathode ray tube. So anybody who is old enough, which is probably only myself and Tara, know about old TV screens where they had actually cathode ray tubes, which were these huge TVs where you actually basically had a tube on the back of it, where you would accelerate an electron and then you would put a magnetic field in there which would change the direction of the electron and then basically would scan across the TV. But anyways, these are called cathode ray tubes. So you have a huge potential difference across these two plates, which in this case is 5,000 volts, which then causes the electron to accelerate. So it wants to know, what is the change in electric potential energy of the electron? And then what is the speed that the electron has when it comes out through these plates? So again, so basically you put a potential difference across here that causes the electrons to Well, actually, what happens is there's a gas on the inside, and that huge potential difference actually strips off the electrons from the gas, so from the gas atoms, which are on the inside. And then the potential region causes the electrons to accelerate through, and then they pop out through here, and then they come and they hit your TV screen, and then this is what generates the picture on your TV screen. So first part is we want to know what is the change of potential energy. So great. So for part A, well, again, we know our change of potential energy is equal to the charge times the change of potential. Here, since it's an electron, we know the charge is equal to negative of the fundamental charge, and we're told that the change of potential is equal to 5,000 volts. So this means our change of potential energy then is going to be equal to negative E times delta V. So this is then equal to negative 1.6 times 10 to the minus 19, all times 5,000 volts, which works out to be I gotta find it. About negative 8 times 10 to the minus 16 joules. So this is our change of potential energy. So now we want to know, once the electron comes out through that region, what is the speed at which it comes out through? So again, let's say here's our delta V region, which has 5,000 volts. Our electron starts off here, so this is our electron. Our electron then is going to feel the force. It's going to be accelerated into this direction, and it's going to accelerate all the way through until it comes out, where now it's outside of the region, so it's going to move at constant speed. And let's say initially our electron starts off at rest, so the initial velocity is equal to 0. Okay. So again, we can use conservation of energy. So conservation of energy says that our change in kinetic energy plus our change in potential energy is equal to 0. So here we then have that our change in kinetic energy is going to be the final kinetic energy, which is 1/2 the mass of the electron times the final velocity squared, minus the initial kinetic energy, which is 0 since the electron was initially at rest, plus then our change of potential energy, which we already calculated up here. So from here, this then tells us that the final speed then is going to be equal to what? Negative of 2 divided by the mass of the electron times the change of potential energy. It's negative since I'm adding or subtracting this term over here. But since our change of potential is negative, we don't have to worry about that. And then take a square root. So this then tells me that, plugging in my numbers, that the final speed is 4.2 times 10 to the 7th meters per second. So the final speed of the electron then is equal to 4.2 times 10 to the 7th meters per second. Okay? Now, so again, as long as I know changes of potential, what'll happen then is I can use that in conservation of energy. But there's more reasons why I actually care about potential energy or potential, and that's because it's directly related to the electric field. So let's talk about the relationship between, so relationship to the electric field. So again, here we know that the change of potential energy is equal to minus the work, which is equal to then minus the force times the displacement times cosine of the angle between the two. But here the force is specifically equal to the electric force. So this is then negative the charge times the electric field times then the displacement times cosine of the angle between the two. But we also know that the potential energy is the same thing as the charge times the change of potential. Now this charge here is the same as this charge, so what this ultimately tells me is that my change of potential is then equal to negative of the electric field times then the displacement times cosine of the angle between the two of those. Now, if we take that, the electric field is parallel to the displacement, meaning that in this case, the angle is equal to 0 degrees. What this tells me then is that what? My change of potential divided by my displacement with a negative sign is actually equal to the electric field. So these are our assumptions. So what this tells me then is what? If I have a potential region, so let's say at this point here, I have a potential of say V1, and at this point I have a potential then of V2, where this happens over a distance of delta x. What this tells me then is that as long as I have a change of potential going from this point to this point, then there has to be an electric field which is present. That's what this thing tells me. So what this tells me is if I know how the potential changes as I go from one point to another point, then this allows me then to determine what the electric field is. And this also tells me the direction of the electric field, where this negative sign says that what? The electric field is in the direction of opposite of the slope, which basically means that what? The electric field then points from the high potential region down to the low potential region, which is exactly what we showed back here initially, where again, that here, my high potential region is the positive sign, my low potential region is the negative sign, so my electric field points from the high potential to the low potential. So all this thing is saying is that if I know how the potential changes throughout a region of space with respect to position, then that tells me exactly what the electric field looks like, where the electric field then points from the high potential to the low potential. So here, if we say that the potential at V2 is greater than the potential at V1, what that means in this case then is that our electric field is going to point from V2 to V1. So this is the direction of my electric field. So ultimately, all this thing is basically saying is that what? If my potential is changing, I have to have an electric field. So if potential changes with respect to position, we must have an electric field. And the electric field points from high potential to low potential. So that means is if I was looking at several spots throughout the space, let's say all of these are separated by a distance of say delta x, but here, if this is at a potential of V, this is also at a potential of V, and this is also at a potential of V, since all of these have exactly the same potential, the electric field in this region must be 0. I have no electric field. So as long as my potential is constant, what that means is my electric field must be 0. I have no electric field. But if my potential changes going from one point to another point over some region, that means I have to have an electric field, where that electric field points from high to low. So the potential then gives me a direct relationship to the electric field. So by measuring the potential, I can then determine exactly what that electric field looks like. So again, so if V is equal to a constant, then my electric field must be equal to 0. There is no electric field. That's okay. So, everyone's okay with this? So ultimately what this tells me then is what? The electric field, or the potential, is more fundamental than the electric field. So potential is more fundamental than the electric field. So if I don't have a change of potential, I do not have an electric field. And at the same time, the electric field is actually more fundamental than force. Because if I don't have an electric field, I also don't have a force. Okay. So now again, this is only true if my electric field is equal to a constant. If the electric field is not equal to a constant, we then have to take a derivative instead. So the fact that E is equal to negative delta V over delta X is only true if E is equal to a constant. But if E is not equal to a constant, in this case, we have to generalize this to the fact that the electric field then is equal to negative of the derivative of the potential with respect to position. Good. Now, using this, what this means is then all objects then are going to create some sort of potential. So what we want to look at now is what is the potential of a point charge? So far we've seen the force between point charges. We have seen the electric field of a point charge. So now let's look at the potential from a point charge. So let's say here's my point charge with a charge of Q. Now, let's talk about this for a little bit. So remember when it comes to potential energy, so for example, if I was thinking of gravitational potential energy, remember, is mgh, where h here is some height above some sort of reference point, which means that if here was, say, the ground, and I was holding my object here of mass m, then I could define h here to be the height from the ground to that point, right? But I can also define the height from the center of the Earth. For example, this could be the center of the Earth. In which case, then the height would actually be this total distance. So this would actually be h, right? So I can define my potential energy that way. So the point of all this is that how I define my reference point creates the amount of potential I have, but usually that region or that reference point is something which is arbitrary. So I could take the ground, I could take the top of my desk, I could take my first floor of my house, I could take the second floor of my house, I could take the center of the Earth. But what matters is the change, not the actual amount of potential. Okay? So when we quote a potential, then we have to all know exactly where that reference point happens to be. Otherwise, the amount of potential that you say an object has is meaningless. So I can say this thing has potential energy of 10 joules, but that doesn't really tell you anything. It doesn't tell you, I mean, that number is basically meaningless. Just because it has 10 joules worth of potential energy, that depends on how I define where my reference point is. So if I define my reference point right here, now this only has 1 joule worth of potential energy. But what matters is how far this thing has actually traveled, because that potential energy is going to convert into kinetic energy. So what matters is the change in that potential energy. So until I tell you where that reference point happens to be, that number of 10 joules worth of potential energy is actually a meaningless quantity. Now, why is that important? Because it's going to be important here when we define the potential of a point charge, because we need to know where the reference point is to be able to say what this number means and what it actually is in reference to. Now, when it comes to a point charge, our reference point is actually going to be way out here at spatial infinity. So R is equal to infinity. So what we're saying is that the potential at R is equal to infinity is 0 when it comes to a point charge. Then if I look at some point closer, so let's say this is the point I'm going to look at, where this is some distance R away, turns out that the potential at that point, so let's call that point P, is then equal to K times the charge of the point charge divided by the distance R. So this is what we call the potential. But what this really means then is that this is the potential relative to 0 at spatial infinity. Okay. So what this is actually telling me is the potential difference between this point in space and spatial infinity where this thing is 0. So that's what this thing is actually telling me. So what it's really telling me is this total potential difference here. So it's really telling me delta V here. Okay. So this is the potential at any point from the center of a point charge to a particular point, which is now K, which again is that electric constant, times Q, which is the charge, divided by R, where R is that distance from the center to that point. Okay. Now, let's talk about some things here. Now, remember that potential energy, is potential energy a vector or is that a scalar? Anybody remember that? So does potential energy have a directional property to it? You're all so quiet. What do you think? Is it a scalar or is it a vector? Take a guess. Tara, what do you think?
I'm going to say scalar.
Great, good job. That's right. So potential energy is equal to a scalar. Good. So this is a scalar quantity, and since potential is equal to potential energy per charge, that means this thing is also a scalar. So the nice thing about potential here, this quantity, is first of all, this thing is a scalar, which means it has no directional property to it at all. So meaning no direction. So here, when we look at potentials, the only thing that matters is the charge itself and the distance at which it is away. Now, notice what's going to be different here than when we do electric fields. So for example, if I was looking at that point, I was talking about the electric field. As soon as I say that the direction of the electric field is here, where you wrote down the electric field, then that was equal to what? K times Q divided by R squared. When I say the direction is positive, we usually put the magnitude on here to make this a positive charge. When it comes to potential, we're not going to do that anymore. The sign of this charge now matters. So meaning if I was some distance R away, if this was a positive charge, then this would have a positive potential. But if it's a negative charge, it then has a negative potential. Okay? So anytime I write down potential, this is always going to be whatever the sign of the charge is. We're never going to put absolute values around it. So if it's a negative charge, we use its negative. If it's a positive charge, we're going to use that it's positive. Now, just like force and just like electric fields, potentials are actually additive. So if I have a whole bunch of point charges, so let's say this is Q1, this is Q2, this is Q3, this is Q4, and I want to know what is the potential at this point. Let's call that point P. Then the total potential at point P then is going to be equal to the sum over all of these different potentials. So I'm going to write down V1 plus V2 plus V3 plus V4, where this is the distance R1, this is the distance R2, this distance is R3, and this distance is R4. So this is then going to be equal to the sum over all of the individual potentials. So the total potential at a given point is then simply equal to the sum of all the different potentials. So let's use this and do an example. So this says, not that one, this one. What is the potential energy at point A here, or sorry, what is the potential at point A in this figure below? So here I have two charges. One is a positive charge, the other one is negative charge. They have the same magnitude of charge, but one is positive, the other one is negative. Point A then is 30 centimeters above the first or the second charge. And then the first charge is 52 centimeters away from the second charge. Okay. So again, I want to know at point A here, what is the potential? So let's redraw. So here is Q2, which was 50 microcoulombs. Over here was charge Q1, which was minus 50 microcoulombs. This distance across here was 52 centimeters. And then some distance above him at this point. Whoops, why did you draw that line? There we go. Good. Was the point A. And we know that this was, what, 30 centimeters, which means that this distance across here was 60 centimeters. Okay. And again, what I want to know is what is the potential at A? Well, according to this, what this says then is the potential at A is simply the potential from charge 1 plus then the potential from charge 2. Potential from charge 1 then is going to be what? K times charge Q1 divided by the distance in this case, which is 0.6 meters, plus K times Q2 divided by its distance, which is 0.3 meters. Now here, Q1 again is negative, and I have to make sure I use that negative. So it's going to be the same thing then as what? Minus 9 times 10 to the 9th times then 50 microcoulombs divided by 0.6 plus 9 times 10 to the 9th times 50 microcoulombs divided by 0.3. So, plug in my numbers, what I find in this case then is that this works out to be about 7.5 times 10 to the 5th volts. Is equal to 7.5 times 10 to the 5th volts. So this is my potential at point A. That was okay? So let's ask a follow-up question to that, which is the next part. So this wants to know then how much work was required to bring Q2 to its final position near Q1 in the figure below. So basically what this is asking was how much work was required to create this charge configuration. So this is what this wants to know. So it wants to know how much work was required to create this charge configuration. So basically, the amount of work it's going to take for us to create this charge configuration is, first of all, the amount of work it takes for us to bring in Q1 from infinity to this point. Okay, so we're going to say initially Q1 is sitting out here. So this is Q1, all at R is equal to infinity. Now we're going to bring this guy and we're going to bring it all the way from infinity and we're going to drop it at this location here. So this is our location we're going to put it at. So first of all, we want to know how much work was done to do that. Then we're going to come out here to, again, spatial infinity, and we're going to pull Q2 from, again, R is equal to infinity. So it's infinite distance away from here. We're going to bring it all the way in and then drop it at this location where these two guys are going to be 52 centimeters away from each other. Okay. This is going to be work 2. The total work then is then equal to the work done by bringing in the first charge plus then the work done by bringing in the second charge. Okay. This is then the total work. So I want to know, again, how much work was required to bring in Q2? So what's the total amount of work here? Right. Now, what we know is that work is equal to what? Negative the change of potential energy. Okay. Or this is then equal to negative the charge times then the change of potential. Okay. So let's think about this. So let's think about work 1. So this is going to be equal to then negative Q1, because that's the charge, times then the change of potential. Now, initially what we know is that what? Q1 is way out here at spatial infinity, R is equal to 0, and what we know is that the potential at spatial infinity is simply equal to 0. So here we know the initial potential energy is simply equal to 0. This is my initial potential energy. So my initial potential energy for charge 1 is equal to 0. Now I'm going to bring this guy in initially here where there is no other charges, which means that its final potential energy is also equal to 0. Since there's no anything there to create a potential, it goes to a region of also 0 potential. So it goes from 0 to 0, which means in this case, its change of potential is actually equal to 0, which means the work done is equal to 0. So that means it took no work for me to move charge Q1 from spatial infinity to this point. Cost me nothing. I did nothing to do it. That was okay? W2, well, the work 2 is then equal to what? Minus Q2 times then my change of potential. Now again, initially what's happening is Q2 is all the way out here at infinity, which means the initial potential for Q2 is also 0. So it's infinite distance away. So in this case, the potential at infinity is 0. So this has 0 potential. So initially it's at 0 potential. Well, now I'm going to take it and I'm going to move it to here. But at this location, there is now a potential, and that potential is now the potential from charge 1. So I'm going to move this thing from a potential to of 0 to a final location where there is a potential, where that potential is simply the potential of the first charge. Okay? Because at this location, there is a potential due to this particular charge. So that means the work done to move in the second one then is going to be equal to negative charge Q2 times the potential at that point from the first charge. Well, since this is a point charge, we now know that what? That potential is simply equal to the electric charge, or the, electric constant, times the charge of that particle divided by the distance r, where this is my distance r between the two. So this is then going to be equal to negative 50 microcoulombs times K, which is 9 times 10 to the 9th, times the charge of Q1, which is negative 50 microcoulombs, all divided by the distance between the two, which is 52 centimeters, or 0.52 meters. Plug in my numbers. What I find in this case then is that the work to bring in the second one is equal to a positive 43.3 joules, which means the total work is equal to 0 plus 43.3 joules, which means the total amount of work is equal to 43.3 joules. So this is the total amount of work to create this charge configuration. So again, the work is simply equal to negative the change of potential energy. So this is the amount of work it took for me to bring in Q2. Now, let me ask you a question. Since the total work, or the work to bring in 2 here, is positive, does that mean that the electric field was the one that did the work? Or did I have to go and do the work? So remember, this is the work. So the work being equal to negative the change of potential energy is the work done by the electric field. So what I'm asking you then is to interpret this. So is the work done being positive, does that mean the electric field did the work itself? Or did I have to go in and grab that charge and put it there because the electric field didn't want to do the work? It's like asking my son to pick up the floor. Did he pick it up, or did I just get sick of him not doing it and then pick it up myself? Which case was it? So what do you think? So does positive mean the electric field did it, or did something else do it? And I picked on Tara last time, so Emma, since you haven't answered anything yet, I'm going to pick on you this time. So what do you think? Did the electric field do it, or did I have to do it? What do you think?
I think the electric field did it.
Good, that's right. So when the work is positive, that means that the electric field did it. Now what would happen is if the work was negative, then that means I had to do it. So if the work was equal to a negative value, that means that something else did it. So an external object did it. Now my next question is, of course, does that make sense? So in this case, since the work was positive, does it make sense that the electric field did it? So what do you think? So does it make sense that the electric field did it? Jolie, I'll pick on you this time. So I haven't picked on anybody else.
Yeah, it makes sense. I don't really know why, but.
Well, let's think about the signs of the charges. So we know that Q2 was positive and Q1 was negative, right? So what does a positive charge and a negative charge want to do to each other?
They're attracted to each other.
They're attracted to each other. So in this case, since Q1 and Q2 are opposite signs, what that means is they want to be as close to each other as possible. So in this case, it makes sense that the electric field did it because they want to be near each other. So this would be negative if both Q1 and Q2 were positive, or if both Q2 and Q1 were negative. So if they were the same sign, in that case, the work would be negative because they don't want to be near each other. They want to be as far away from each other as possible. So I would have to come in and physically force them to be near each other, which is opposite of what the electric field wants to do. So in this case, it makes sense that that it's positive because it's a positive charge and a negative charge, and they want to be as close to each other as possible. Good. There we go. Yeah, you guys are answering all kinds of questions correct today, so that's good stuff. Everyone's okay? So, last thing we're going to talk about today is, first of all, why this room is so hot, and then second of all, what we call equipotential surfaces. So let's talk about some equipotential surfaces. So what's an equipotential surface? Well, again, we already saw this in lab, but let's talk about it a little bit more formally. So an equipotential surface, or lines in 2Ds. So a surface would be in 3D, or we can call this equipotential lines in 2D, are surfaces or lines, depending on what dimensionality we have, of constant potential. So basically, anywhere across the surface or across this line are positions where the potential is exactly the same. So we have constant potential. Now, what does that tell me? So what that tells me is what? So let's say this is my equipotential line. So that means that at this point here, 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 all have exactly the same amount of potential. Now, since the potential is the same, what that tells me then is that the change in potential going from one point to another point is simply equal to 0. So anytime I move across this equipotential surface, if I start at this point and I move to this point over some distance of delta x, I'm at the same potential, so my change of potential has to be equal to 0. But since work is equal to negative the charge times the change of potential, what that means then is the work I do to move this thing from this point to this point is simply equal to 0. So that means I can move this thing anywhere from any cross tier on this surface by doing no work. Or even if I took my object and I move it all the way down here, all the way around like this, and I end up somewhere on this line, the amount of work it took for me to do that is 0. So anytime I move it from a point on the surface back to that surface, or a point on that line back to that line, the work has to then be equal to 0. Now, why is this more important? Well, this is more important because my change of potential then, which again is equal to what? Minus my electric field times my displacement times cosine of the angle, this tells me something further about the relationship between the potential and the electric field. And what does that tell me? So what this tells me is, if I have a potential, or if I have an electric field, I have to have a change of potential. And if I go from this point here to this point here, I have a non-zero displacement, which means if this thing is equal to 0, in general, my electric field is not going to equal 0. My displacement that I moved it is also not equal to 0. So the only way to get this thing equal to 0 is if the cosine term is equal to 0. So the only way I can have that's what? Again, my work being 0 or my change of potential to be 0 is if in this expression, where in general I have a non-zero electric field and a non-zero displacement, because I'm not staying at the same point, the only way to have that true is if cosine of the angle is equal to 0. But where is cosine equal to 0? So for what angles is cosine equal to 0? So what do you think? Looks like I'm back on you, Tara, so I'm going to pick on you. So where is cosine equal to 0?
At the origin?
What do you mean by origin?
I'm not actually sure. I'm just throwing something out.
Fair enough. So think about in terms of angles, right? So if I was thinking about a unit circle, for example. So where is cosine equal to 0 along a unit circle? So remember, cosine basically means the horizontal direction here. So that's going to be either this position or this position. So you're right at the origin. So that's why I just wanted you to kind of explain it a little bit more in terms of angle. Well, it's this angle, right? Or this angle, which means it's either 90 degrees or 270 degrees. So you were right. Go a little more confidence, we'll be good. So basically what this means is the only way to have this equal to 0 is if the angle is 90 degrees. Okay? Because that's where cosine is equal to 0. So what this ultimately tells me then is that what? The relationship between the electric field and the potential is not only changes the potential tell me about the electric field, but it also tells me how the electric field has to be oriented to these equipotential surfaces. So what this says then is that what? My electric field must be perpendicular to these equipotential surfaces. So typically what we would do then is what? If we have some sort of charge configuration, we can go in and measure these equipotential surfaces. This is what you did in the lab. And then by knowing the equipotential surfaces, so let's say this is one potential surface, this is say another potential surface, let's put another potential surface say here. By knowing these equipotential surfaces and knowing the fact that the electric field has to be perpendicular to it at all locations, let's say here, here, and here, 90 degrees here, 90 degrees here, 90 degrees here, 90 here, 90 here, and 90 here. This will then allow me to map out my electric field. So in this case, my electric field has to go, say, like this, and go like this, and go something like this. And since the electric field points from high potential to low potential, what that also tells me then is what? If I know, for example, that the black line here is at, say, 2 volts, the green line here is, say, at 1.5 volts, and the blue line is, say, at 0.5 volts, then that tells me the direction at which the electric field is pointing as well. It's going to point from the high potential to the low potential. So by mapping out these equipotential surfaces, it allows me to determine exactly what the electric field looks like, because it has to be 90 degrees at every location relative to a equipotential surface. These are all at 90 degrees, and it points from high potential then down to low potential. Now, why is this important? Well, this is important because, first of all, again, the potential is a scalar quantity, which means it's a lot easier to measure a scalar quantity as opposed to a vectorial quantity. Also, when you're talking about mathematically, it's also easier for me to deal with something which is a scalar as opposed to something which is a vector. This is also important because it's much easier for me to measure a potential. That's a voltmeter. What a voltmeter does is it measures potentials, so it's a lot easier for me to measure a potential as opposed to an electric field. We actually don't really have devices that measure electric fields. So by using a voltmeter, so here's my voltmeter, by putting one prong, say, here, and putting another prong here, where this is at, say, 0 volts, and this is at 2 volts, and then I can measure all locations at exactly 2 volts to create now this equipotential surface. What that does is it allows me then to determine what does the electric field look like throughout the entire space without actually ever being able to measure that electric field. And since potential is a scalar quantity, it's a lot easier for me to deal with that as opposed to a vectorial quantity. So this is why we pay mostly attention to potentials, because potentials are scalars. They're easier to deal with mathematically as opposed to, as opposed to vectors, or in this case, electric fields, which are vectors. It's a lot easier for me to measure. I have a voltmeter which is designed to do that. I don't really have anything designed to measure an electric field. And it's intimately related to the electric field because by knowing how the potential surfaces are aligned, that determines exactly what the electric field looks like. So this is why we actually spend so much time talking about potentials and why we deal with potentials so much. So let's kind of do an example of this and let's draw some equipotential surfaces and see what we can tell about something. So let's say I have equipotential surfaces that do something like this. So here's one surface. Here's another surface. And let's say here's another surface. And what I want to know is, what does the electric field look like, and what can I tell about the particles? So here what's really happening is that here there's one charged particle. Here there's another charged particle. What can this tell me about my charged particles? So what haven't I used yet? Blue. So again, the way we would do this is we would just draw some 90-degree angles. So here's a 90, here's a 90, here's a 90, 90, 90, 90. This would be 90, then a 90, and then a 90. And then we're basically just going to connect these lines together. So I have one would go in this direction, one would go this way, one would kind of fan out like this, one would be here, and then here, and then here. So this would kind of fan out in this direction. Here, here, and here. So this would kind of fan out this way. On this side, I have a 90 here, 90 here, and a 90 here. So this would also fan out this way. And then a 90, a 90, and a 90. So again, this would fan out like this. So basically, if I followed all these 90s, I would have something that would end up looking like this. Now, again, without knowing if this is a high potential, so without knowing that, I couldn't tell the direction of the electric field lines, but at least I can tell what they're doing. Now, what can you tell me then about these two charges? Are these oppositely charged, or are they the same? Are they like charges? So does one have, say, a positive charge, the other one has a negative charge, or are they both, say, positive or both negative? What do you think? Looks like I'm back to picking on Emma. Emma, what do you think? Are they like charges or unlike charges? Based off electric field configurations we drew before.
Would they be unlike charges?
Almost. They're actually like charges. So remember that when we draw like charges, the electric field lines have to diverge away from each other, where if they're unlike charges, they have to terminate. So they originate on one, terminate on the other one. So in this case, by again looking at the pattern of my potential surfaces, what that will tell me is, what are these charges? At least how are they related to each other? Now, if I knew this was again at say 5 volts, this was 3 volts, and this was 2 volts, then I would know that my electric field lines were doing this, which means not only are they like charges, but they are positive charges. So that brings us back to this kind of simulation that we brought up here. So here again, if I had double lines, if I draw the equipotential lines, again, we can see this gives us the same pattern that we basically drew. Right? So we're seeing these lines around the outsides. So here we know that these guys are, and now the field lines are diverging away from each other because of those. And again, if I draw my vectors on here, since these are positive signs, these have to be high potential regions down to low potential regions. As opposed to, if I was dealing with, say, a dipole, if we look at the equipotential lines here, so here it gives you more of a circle type eye, owl eyes, basically. Right? So in this case, what's happening is I'm going from a plus to a negative, so I'm going from a high potential down to a low potential, so I have to cross through 0 at some points. Right? So that has to happen in the center. So here, if I draw my lines, so my lines have to start on one and terminate on the other one. Or then if I put in the vector signs, it's going to point from the one to the other one. So this is the utility then of these equipotential surfaces. So the equipotential surfaces tell me regions at which I do no work, where I have 0 change of potential, but more importantly, what they tell me is, what does the electric field look like throughout the entire space? So by knowing and mapping out these equipotential surfaces, what that tells me, again, is that the electric field has to be perpendicular to all of these equipotential surfaces. So at any point along this equipotential surface, the electric field has to be 90 degrees relative to that surface. So again, by looking at all of these surfaces, I know exactly what my electric field looks like. And then by knowing what's high potential and what's low potential, that also tells me the direction of the electric field, because the electric field points away from high potential. So it points from high potential then down to low potential. Okay, he always points from high to low potential. So this is the utility, again, of these equipotential surfaces. By knowing what they look like, and again, these are just surfaces where they have exactly the same amount of potential, then I can map out, again, my electric field. So that means that for a point charge, if this was my point charge of Q, the equipotential surfaces are simply circles. Right? Everywhere along here, this is then simply the same amount of potential. So any point along this circle of constant radius is my equipotential surface for a point charge. Once I start combining these together, it becomes a little more complicated. So let's do a couple more examples of these. Let's try, not a double row, let's just do a row. So here, again, if I do equipotential surfaces, again, it shows me what the surfaces look like. And again, the electric field has to be perpendicular to all of those lines, which causes this, again, to kind of diverge outward. Okay. So these are my equipotential surfaces. So that's the end of the first half, basically this chapter. So starting tomorrow, we will finish off this chapter, and we're going to start talking about capacitors, which was, what, 2 labs ago now. So we're going to start talking about those, how those work, how we charge those up, energy storage, and all that kind of good stuff. So yeah, so that's what we'll do tomorrow. And again, this is up on Blackboard, so go ahead and play with this and kind of, again, get a little better feel of how all this stuff kind of works. But yeah, so otherwise, any questions anybody has for today? If not, we'll kind of stop a little bit early. But doing okay? I'm assuming everybody else's power went out. That's why nobody else is here. Unfortunately, there's only the 3 of you. So I got to pick on you all the time, but it's fine. Keeps us honest. There we go. All right. Okay. Well, if that's it, then I will see you all tomorrow. Hopefully some more smiling faces as well. Tomorrow will be great, but we'll see what happens. So otherwise, have a good night, and I will see everybody tomorrow.